This video covers a brief review of matrix or linear algebra as it applies to finite element analysis. Before our review, let's talk real quick about why we need matrix algebra in FEA. And there are two main areas. We need it to formulate the problem for finite element analysis, but we also need it to solve the problem once it's formulated. When we're formulating the problem, we need to come up with a system of equations that relate stress and strain. We need a system of equations relating strain and displacements, and we need another system of equations that relates displacements and degrees of freedom. I'll talk more about degrees of freedom later. We're going to put all of those together to form something called a global system of equations, which has a global stiffness matrix, the K listed in this equation. So this is going to typically be a very large system of equations, and that brings us to the problem solution. When we're solving the problem, we want to solve simultaneously a large number of variables, being our degrees of freedom, and using a large number of equations, the global system of equations. In order to do that, we want to take advantage of linear or matrix algebra solution techniques, which are rigorous, general, and efficient. Let's get started with some matrix notation. So first of all, the terminology of an m by n matrix means the first number represents the number of rows in the matrix, and the second number represents the number of columns. So a 2 by 3 matrix would have 2 rows and 3 columns, as shown. Matrices can be used to represent a system of linear equations. So for example, the 3 equations shown here, these are actually the notation that we will use in FEA. K represents a stiffness term, D represents a displacement of some variety, and F represents a force or a load of some variety. So I have a system of 3 equations. I can write that in matrix form by pulling out all the coefficients of the displacements, and then have a displacement vector and a force vector. Then I can simplify that to just be KD equals F. That's our basic FEA equation. Okay, let's talk about some matrix terms. First of all, a diagonal matrix. A diagonal matrix has the only non-zero terms are on the diagonal. Everything off diagonal is 0. In additional notation, A sub ij, where A is a component of the matrix, is equal to 0 if I and j, the row and the column numbers, are not equal. Or in other words, this is an example of a 4 by 4 diagonal matrix. A symmetric matrix is another type. A symmetric matrix is a matrix in which the terms are mirrored across the diagonal. So a symmetric matrix doesn't impose any rule on the diagonal itself, but the terms above and below the diagonal are mirrored. In other words, Aij equals Aji, again with additional notation. So this is an example of a symmetric matrix. As you can see here, the B is mirrored, the C is mirrored all across that diagonal. And the last term on this slide is matrix transpose. In the matrix transpose, what we're doing is we're swapping the rows and the columns. So the first row of a transpose matrix becomes the first column when we perform the transpose. Now let's talk about matrix determinants. A matrix determinant is a scalar that comes from a square matrix. It's some measure of the size of the matrix, if you will, not the dimensions, but the terms inside the matrix. You end up multiplying a lot of terms to get to a matrix determinant. The reason that they're relevant for finite element analysis is that we can use them to determine if the underlying system of equations, assuming that the matrix represents the matrix of coefficients, then if the determinant is 0, then that tells us something that we don't want to know. It tells us that we do not have a unique solution to our system of equations. So this is a useful thing to be able to calculate for a matrix. For a 2 by 2 matrix, it's pretty straightforward. Let's imagine we have this ABCD matrix. The determinant involves calculating first the diagonal terms AD, and then subtracting out the cross-diagonal terms BC. That's the determinant of a 2 by 2 matrix. 3 by 3 matrix is kind of similar to that. You can also use the diagonals. So go down the main diagonal, we get AEI, and then we continue to go down the diagonals, but we have to have a complete diagonal. So BF, and then we have to go grab G. And then C, but that has to go with D and H. So those give us our first 3 diagonal terms in the positive direction, and then we get 3 diagonal terms in the negative direction. So A requires F and H to complete a diagonal. BD requires an I, and then finally CEG. And all of those are negative diagonals because they're heading off in the opposite direction. If you're trying to find the matrix determinant for a larger matrix, let's see what happens if we do this on a 3x3 matrix. It works for 4x4, 5x5, and so on. We can use something called cofactors. So the idea of this is that we take a term in the matrix. Let's pick A11. Then it has a cofactor, which are the terms in the matrix that are not in the same row or column as the term AI. So the cofactor is this smaller matrix here. In order to use that, we take the term AI and we multiply it by the determinant of the cofactor. So that's A22, A23, A32, A33. But then we need to pre-multiply it by a -1 to a power. And the power is the sum of the row and column number for the original term A11. So in this case, it's -1 to the 1 plus 1 power. Of course, that's just 1. Continuing on, we just go ahead and move to the next term, A12. Its cofactor then consists of A21, A23, A31, A33. So we have the product A12 with A21, A23, A31, A33. And then out in front of that, we get the -1 to the 1 plus 2 power. So that's to the 3rd power. That gives us a negative on the A12. And then the third term, A13, gives us its cofactor, A13 times its cofactor, A21, A22, A31, A32. And it's pre-multiplied by -1 to the 1 plus 3. So that's the 4 power. So that's a positive 1 as well. Let's talk about matrix inverses. A matrix inverse is the matrix that, when multiplied by its original matrix, yields the identity matrix. In other words, 1's down the diagonal and 0's everywhere else. The matrix inverse is very useful to us in terms of solving finite element analysis problems. So we need to know how to calculate a matrix inverse. Now, the code's going to take care of that for us when you're running finite element analysis, but we want to understand what it's doing in the background. So I'm going to show you a process to find a matrix inverse. So to find it, what we want to do is pair the original matrix with the identity matrix. I'll show you that in just a moment. That gives us a double-wide matrix, and then we can use row operations to convert that original matrix to I. The new matrix on the right is the inverse. So you'll see in just a moment what I mean by that. And just as an aside, an orthogonal matrix, another useful term, an orthogonal matrix is a matrix whose transpose is also its inverse. Okay, let's do a quick example on finding a matrix inverse. Okay, let's find the inverse of this matrix. B is equal to 2, 1, 3, 4. We're going to take the matrix 2, 1, 3, 4 and we're going to pair it with the identity 2 by 2 matrix, because this is a 2 by 2. And we're just going to put that vertical bar down the middle there to indicate the two matrices. So what we're going to want to do is apply row operations so that the left-hand side becomes identity. The right-hand side will then be the inverse. So the first thing I'm going to do is divide row 1 by 2. And that just gives me a 1 in the first term there. And that's my pivot term now for moving forward. Next, I'm going to subtract 3 times the first row from the second row. The row operations allow us to subtract rows from each other, add or subtract. So that eliminates the 3 in the lower left term, which is nice. It's getting me closer to the identity matrix. But of course, things are getting a little bit more messy. As we can see here, we end up with 4 minus 3 halves, and then a negative 3 halves, and then the 1 is unchanged. Next, I'm going to try to improve that second row. First of all, I combine 4 minus 3 halves, and that's going to give me 5 halves. So I then divide by 5 halves, which gets me a 1 in the lower right term of the left-hand matrix. So divide all of row 2 by that 5/2. That gives me a minus 3/5 and then a 2/5 on the right-hand matrix. But we're not done yet. We've still got a 1/2 in the upper right term. So I'm going to subtract 1/2 times the second row from the first row. And lo and behold, I now have a identity matrix on the left-hand side. And the right-hand side is a little bit messier. I've got 4/5, negative 1/5, negative 3/5, and 2/5. So that tells me that the inverse of B is 4/5, negative 1/5, negative 3/5, and 2/5. If we check this, take B times B inverse or B inverse times B, it can go either way, we will get the identity matrix. Note that there's a bit of a shortcut here. For a 2x2 matrix, actually it's a huge shortcut, for a 2x2 matrix, B11, B12, B21, B22, the inverse is automatically 1 over the determinant times B22, negative B12, negative B21, and B11. So in other words, it is 1 over the determinant, and then we swap the diagonal terms, and then we put a negative sign in front of the off-diagonal terms. And that gives us the inverse of a 2x2 matrix. How do you add and subtract matrices? Well, it's pretty straightforward. You just do it term by term. So suppose I've got these two matrices, A, B, C, D, and E, F, G, H. If I want to add them, first of all, we need to check to see if we can add them. The number of the rows and columns must be equal in order to add them. They don't have to be square, but they have to have the same number of rows and the same number of columns. So to add them together, I'm going to take the first term, upper left term in each matrix, add that together. That gives me A plus E. Then I'm going to take the top right term from each matrix, gives me B plus F for the top right term in the sum. And then the lower left term, C plus G. I'm going to then take the lower right term, D plus H. And that gives me my summed matrix. For subtraction, same thing, except we just have a negative 1. Let's talk about matrix multiplication. Suppose I want to multiply these two matrices, A, B, C, D, and E, F, G, H, I, J. First question, of course, is can I multiply these two? Now, I've got a 2x2 matrix, and I'm trying to multiply it with a 2x3 matrix. The rule is, if the number of columns in the first matrix is equal to the number of rows in the second matrix, then yes, I can multiply it. So I'm okay here. Then I want to figure out what I get at the end. I'm going to get a matrix, but what size is it? So it turns out that the number of rows of the first matrix determines the number of rows in the product, and the number of columns in the second matrix determines the number of columns in the product. So I'm going to end up with a 2x3 matrix at the end. So how do we go about multiplying them? So got the two matrices here again. I'm going to take the first row of my first matrix and multiply it by the first column of my second. So I get AE plus BH. And then I'm going to have other terms here as well to fill out the 2x3 matrix. Secondly, I'm going to take the second row of the first matrix and multiply it by the first column of the second matrix. So that gives me my second term, CE plus DH. And I just continue this process, going back and forth the rows of the first matrix and multiplying them by the columns of the second matrix. So I end up with a complete 2x3 matrix as shown here. There will be times in FEA when we have to apply calculus to matrices. So what do? Well, it's pretty straightforward actually. To take the derivative or the integral of a matrix, you simply take the derivative or the integral of each term of the matrix. So it's term by term calculus. So in other words, if I want to take the derivative of this 2x2 matrix F11, F12, F21, F22, if I do a d by dx on that, I'm just going to bring the d by dx inside. So I have the derivative of F1, 1, the derivative of F1, 2, the derivative of F2, 1, and the derivative of F2, 2. Same thing with the integral. If I take the integral of the matrix, that same matrix, I'm just going to take that integration inside the matrix and do it term by term.